So in this lecture, we will discuss about what is the phase difference between direct and reflected path. So I will show you in the figure. So you can see here, this is a mobile unit, which is at H2, and this is below the ground level H2. So you can see both this H1 plus H2 is the height of the total height, and this is the direct wave from the antenna towards the mobile antenna, and this is the reflected wave from the antenna towards the mobile. So this is the angle theta and this is the angle phi, and this is the distance d between the antenna and the mobile. Okay, now we will see what is the phase difference between direct and reflected path. So based on direct and non-reflected path, as I show now, where direct path is a line of sight path, there is no obstacle, it is received power. So the loss of the power, the line of sight path, so the received power is equal to transmitted power into 1 by 4 pi d by lambda whole square. So on a ground reflected path, this reflection coefficient and phase change after reflection is the sum of two wave paths will be added. That is expressed as the received power is equal to the loss of the power. The received power is equal to transmitted power P naught into 1 by 4 pi d by lambda whole square. So into 1 plus AV into e power j del phi whole square. So alpha AV is the reflection coefficient, del phi is the phase difference between direct and reflected path, P naught is the transmitted power, D is the distance between the antenna and the mobile unit, lambda is the wavelength. So this indicates this equation the received power of the after the reflected path. So after simplifying the equation 2 is the equation for a two-wave model, which is used to understand the path loss phenomena in a mobile radio environment. So it is not the model for analyzing the multipath weighting phenomena. In a mobile environment, AV is equal to -1 because the small incident angles of the ground wave caused by a relatively low cell site antenna height. So if you substitute the value and if you simplify this equation, what is here? You are having 1 plus AB into e power j del phi. So if you simplify e power j del phi, we can get as cos del phi minus j sin del phi. And after simplification, we are getting as this is the equation where we know that del phi is equal to beta into difference of d. So the difference of d is d1 minus d2. So d1 is equal to h1 plus h2 whole square plus d square, and d2 is equal to h1 minus h2 whole square plus d square square root. So because delta d is much smaller than either d1 or d2, you can take del phi is equal to beta delta d, that is 2 pi by lambda into 2h1 h2 by d. Okay, this is all the simplification analysis. So then the received power becomes, we are substituting the previous equation. If del phi is less than 0.6 radians, then sine of del phi by 2 is equal to del phi by 2. That is cos of del phi by 2 is equal to 1. This is a trigonometry that you have to remember. And the above equation simplifies to, you can get this finally P naught into h1 h2 by d square whole square. So from the above equation, we can reduce two relationships. That is delta P is equal to 40 log of d1 by d2, a 40 dB per decade path loss slope, and gain delta G is equal to 20 log h1 dash by h1, and antenna height gain of 6 dB per octave, where delta B is the power difference in decibels between two different path lengths, and delta G is the gain in decibels obtained from two different antenna heights at the cell site. So from these measurements, the gain from a mobile antenna height is only 3 dB per octave, which is different from 6 dB for h1 dash shown in the equations. Therefore, the gain is equal to 10 log h2 dash by h2 and antenna height gain of 3 dB per octave. So this is about the phase difference between direct and reflected path.